Alright, today's chapter is dealing with the modern atomic theory. Now, what we mean by modern atomic theory is we're going to actually help understand more about why the periodic table is set up the way it is, how the electron configuration, and that's the arrangement of those valence electrons, can really help explain what's going on with some of the molecules, and where that comes from, where this whole idea comes from. So we have to look at how the atom itself is put together, and how the electrons actually orbit those atoms. Alright, now, a little bit of history. We've seen this before. Where our subatomic particles in the chemistry world are, we have our protons, neutrons, and electrons. Got their rough charges, their locations, and their relative masses. Now, protons and neutrons are not exactly the same mass, but they're both close enough to 1. It's like 1.007 for the proton, 1.008 for the neutron. So there is a slight difference, but it's not substantial. And the electrons make up almost no mass. Alright, the concept of how the atom is put together was kind of predicted, or at least cleaned up on our ideas back in 1911. Ernest Rutherford actually bombarded a thin piece of gold metal. It says thin metal here, but it was actually gold. They used gold because you can get it really thin and it's still actually intact. But bombarded that gold with alpha particles. Now, alpha particles are radioactive particles. They are very energetic nuclei of helium atoms. They're just got a lot of energy to them. And the belief prior to Rutherford was that since this was a very thin piece of metal, that most of these alpha particles would just go right through. Because the only particle that was expected to be there was the electrons, which are that 0.005 AMUs. They were viewed as being so small, it was expected the alpha particles just bowl right through them. But actually what they did is they started bouncing back, and that's simply because gold actually has a nucleus with all the protons and neutrons very condensed. Those alpha particles were occasionally hitting those nuclei, and that's what caused them to fly back. Yeah, some of them did go through, but others bounced completely straight back. But now that we had this data, that gave us a much better idea that the atom was made up of a nucleus, which had all the mass, and then the electrons were around the outside of it. Okay, so we have a whole idea now. We know that the protons, which is most of the positive charge, or all the positive charge, and the neutrons, which are neutral, are in the nuclei. And we know that the nuclei is very small compared to the space the electrons take up. Alright, so knowing that doesn't really help us a lot, because we want to know a little bit more what the electrons are and how they're arranged, how they move, and more importantly, does it help us understand what's going on in the atom with regard to energy and light. Alright, that latter part's kind of interesting. So it turns out all atoms have a unique way of reacting to visible light. Like this spectra down here, I know you can't read it. It's actually an infrared spectra. It's actually looking at the infrared light, and it's of an alcohol. And it turns out almost all alcohols have this big, huge hump right here. And we know that that hump is happening because of OH bonds. OH bonds actually show up there. Matter of fact, if this had been water, you'd have that same peak. So those bonds are showing up at a very particular color. Well, that's interesting. Why does a bond give a wavelength of light? But we see this even in nature. I mean, chlorophyll is green, and we see that the leaves reflect that green light. We see a lot of things. So what is it about the atom that does that? Alright, before we go to that, let's explain what we're talking about with light. Now, in general, the big technical term for light is electromagnetic radiation. Now, technically, this covers way more than just the visible light you see in the infrared we just saw. The spectra for this, I'm going to skip a slide, is huge. We have gamma rays all the way to radio waves and everything in between. These are actually light waves or electromagnetic radiation. Now, it turns out no matter where on the spectra you are, so all those lists, all those little numbers at the top and bottom, they are all related to one another with this wonderful equation right here. The speed of light is a product of the wavelength times the frequency. Now, frequencies are almost always given in units of per seconds or hertz, Hz. Wavelengths do change. Most of the time they are in meters, or most of the time they are in nanometers when we're talking about visible light, but the units do change quite a bit on wavelength. So we'll see that when we actually practice some of these. But they are all interchangeable. That speed of light keeps this constant, which means the wavelength and frequency are always related. Which is why on this chart they are kind of fixed. So that 4 times 10 to the 7th and that 10 to the negative 12 thereabouts are fixed. What's different is where they show up in the spectra. So our high energy gamma rays have a very small wavelength, but a very large frequency. All right, now it's wanting to know which of these has the lowest frequency. So wavelength goes up as we go to the right, frequency goes up as we go to the left. So if we want lowest frequency, we're down over here. Low frequency, high wavelength, that would be radio waves. All right. We can actually relate those on almost any case by actually giving you one of the two. So the practice problem down here at the bottom, I tell you that a FM 95 radio station actually broadcast at 95.1 megahertz. So 95.1 times 10 to the 6th hertz. And we want to know what the wavelength of that light is. And we're going to get the wavelength in actual meters. All right, so we are just going to use this equation, the C equals lambda nu, wavelength times frequency. We know the speed of light because I give it right there. Meters per second. We're going to solve for the wavelength and our frequency. And I could put this 95.1, and instead of putting mega, times 10 to the 6th hertz, which are per seconds. And that's actually what I'm going to put into my calculator here. So, got to move my calculator. So I'm going to start with that 2.998 times 10 to the 8th, and then I will divide by the 95.1 times 10 to the 6th hertz, and I get a wavelength of 3.15 meters. Now, want to see how I put that in? So the E's are that times 10, and practice that with your calculator you're going to use because you want to make sure how that works. But look how neat that is. So an FM 95 wavelength, so standard radio waves, that size of the wave is 3.5 meters long. So it's a huge wave. It's actually, if you could see it, it's pretty long. All right. Now, how does that relate to our spectra, though? All right, because we know that the light is a wave, because we can actually do various different studies for those, but why do certain atoms give different properties? Why do certain molecules give different properties? What I mean by that, I'm going to go to this nice little picture here. So visible spectra down here, the rainbow, that's what we get if you were to like shine the sun through a nice little prism. You get that little rainbow effect. Well, we can actually make lamps. That's what they're showing here. See this little pink light? All that is that was a pure hydrogen gas in there with some electrical discharge going through there. So it's pure hydrogen gas. They run a current through there, high voltage current, and it glows pink. You probably heard of neon bulbs. Well, neon bulbs don't necessarily have neon in them, but by changing the gas in them, you get different colors. And that reddish pink is what you get if you actually put just hydrogen, in there. Now, what's weird is, if I were to run that pink thing through there, I don't get any pink wavelength over here. That's why you don't really see pink here. Pink is a result of a blend of colors. You get 4 main bands. That's that red there, this green, a blue, and a slight purple one. You get just those. That's all you get. Now, if you change the gas, mercury gives a different color. Strontium gives yet a different color. Mercury actually ends up looking mostly blue, well, purple, and strontium actually looks mostly red. But all those wavelengths are in there. It's just that certain ones are a little bit more noticeable, a little bit more intense, at least for us to observe. All right, but everything is somewhat different. All right, so that was something they wanted to understand what was going on. Why were atoms creating these lights when we just added electricity to them? All right, so it must be something about the atom itself. Now, we actually can take advantage of it and see it in many cases, but we want to know why it is. Why is that spectra unique? All right, so early scientists, when they're looking at this, started actually realizing things. The first guy who came up with anything that was groundbreaking and it stood the test of time was this guy Max Planck. Now, he didn't actually try to explain perfectly what was going on with that light yet. He actually just said the light was coming off in certain quantities. So that was a little bit weird at first, because waves are just like ocean waves. There's big waves, there's small waves. Max Planck here was somehow saying that that wave was an amount. It was something physical. It was a stream of actual particles. Now, it's all well and good, but it was the actual basis of the quantum theory. And at first it wasn't fully accepted. It was just more that it eventually becomes more provable as we go along. But it was just an idea at first, a theory. All right, now his equation actually relates the energy being emitted or being absorbed to the frequency itself. Not the wavelength, the actual frequency. So you remember we said that you put energy in to an atom and it gives off light? That's where he was coming up with that. That somehow that frequency was related to the energy going in. And it wasn't giving us all random energies. It was giving us very fixed ones. So very certain amounts. So therefore, Planck said, well, the energy is quantized. It can only come out in fixed amounts. All right, so what does that mean? It actually kind of means that this right here is related to something in the atom that's a change of energy. And it's different, this is different, and this is different, and this is different. So there's two different energy changes in the atom. And when we go from one level to another, it changes the energy level. Now, what we're going to do, let's just kind of rotate this sideways. See how this suddenly kind of looks like maybe a weird bookshelf? What Planck was saying, if I put energy into this system, I have to move a book up to an upper shelf. And I can do that with almost energy in. I just put energy in and the books will move up higher. But when the energy is released, that book can't actually stop halfway through. It has to go down to either the next shelf or the next shelf or the next shelf. It's very limited on how it actually can be given out. Now, it turns out it's actually limited on what it can absorb. We weren't ready to be able to prove that yet. But the energy being absorbed is being absorbed in certain amounts as well. But that coming back down, that's why we see these distinct lines, because there's only certain amounts that are allowed to occur. There's only certain changes that can happen. All right, so what's going on with the atom that actually puts these restrictions in there? All right, so we got this whole idea that something in the atom is a bookshelf type thing. And we have a bigger gap between the smaller ones, and as they go up, they get closer and closer together. But we want to know more about why that is. All right. The first person that gives us a good model takes Planck's revelation and relates that energy to the frequency of light and expands it to those energy levels. But instead of saying it's bookshelves, he says those are quantum levels. So we're going to go ahead and put these back up here. And this is somehow a quantum level now. Now, we're not defining what that is yet. We're just saying that the energy of the atom itself is somehow quantized to a quantum level. And when we move energy to and from one quantum level to another quantum level, it either takes that energy or it gives it off, but it's very fixed amount. So the reason the light is quantized in what we see is because the atom itself is quantized. And every atom gives slightly different colors because every atom is slightly different. All right, so Bohr has this idea, and he fully makes a full model that works perfectly well for hydrogen. Technically, it works for helium as well, but it needs to be helium with just a single electron. And theoretically, lithium with just one electron would also work. All right, so it had to be just one electron to get this full model work. Anything else, it totally falls apart. Yet, Bohr was able to prove it really, really well with hydrogen. It used Planck's numbers. It brought in some things that Albert Einstein said, and it just got a lot of people on board with what was going on with the quantum levels and the atom itself. But it creates some new terms. So ground state in a hydrogen atom doesn't mean no energy. It just means a minimum amount of energy. So think about, so go back to our little bookshelves. Technically, when we're at this bookshelf, the atom is still exhibiting energy because the electron's still moving around. And that is what they mean on the ground state here. It's still moving, it hasn't stopped moving, and it won't. But all we're going to do when we move it up to excited state is put more energy into the electrons in that orbital cloud. So the electrons are what's creating these quantum levels. And the further they move up, the more energy they have in them. Okay, so got this wonderful picture. These lines are related to the lights being emitted and the energy levels of an atom, hydrogen atom in this case. Now, this doesn't mean that this is an energy level. This is the result of the change between two energy levels. Energy level 1 going to energy level 2, or I'm going to say A and B because we're not going to define what the levels are. There is just a change goes on, and when that electron moves from one orbital to another, it emits that red light. That energy difference is red. All right, so Nobel comes out and gives Niels Bohr a prize, Nobel Prize for this back in 1922. And yet the irony is, even when he came out with it, the only thing this model worked for was hydrogen. So all the other atoms in the periodic table we have no model for whatsoever, but this gets us on the right idea. All right, to take us to the next level, we got to actually look at what those quantum levels are, because clearly they're not bookshelves. Whatever this quantum level is, there's something about how the electron moves in that level. All right, the idea put forward at first was that those quantum levels are somehow orbits. Well, that works, and it also explains why this wouldn't necessarily work for, like, say, helium. And the reason it doesn't really work for helium, on Bohr's model, with one electron, the electron can move back and forth between any one of these levels, and the only thing that's really interacting with it is the nucleus itself. Very positive charge repelling those electrons. So that single electron does a very predictable behavior. But if we're over here on this guy, with a lot more of these electrons, that's what the little red dots are. If I want to move this electron into the previous orbit, I have another electron there that's repelling it. And yet if I'm over here, this one doesn't have one nearby as much. So you see how the other electrons have to enter into the play? Well, that's what's going on in any other atom. The other electrons are actually adding to the complexity of the math. So while Bohr was able to come out with a nice equation that has the delta E in it, and it's actually related to just these ends. Matter of fact, it's a weird equation. It's got this. We won't be using this. I'm just putting it up here because it's kind of neat that the energy levels that Bohr actually described just has this number in here. Got a unit here. And then these little n values, they're just subscripts. So if I wanted to figure out the energy difference between this, the blue arrow right there, I put a 3 here, and I square it, and I put a 2 there, and I square it. And I just solve for it, and I have the energy difference. Works perfectly fine. But as soon as I get to a real atom with more and more electrons, this formula is totally useless. So we're not even actually going to try to use it. Bohr actually got us on the right start, but now we have to take it further on. All right, now the biggest problem is it does neglect those other electrons. It also assumes that we know the path the electrons take. Well, that last part is just absolutely wrong. Matter of fact, we absolutely know that it's not in an orbit. And that has a lot more to do with how the energy would have to be exerted. So it's not a circle. All right, what they're going to do to actually figure this out is they're going to start treating the electrons as having wave-like particles. So you know how we said at first light was definitely a wave, and then we started talking about how it was like a particle and it had certain amounts being released? We're going to do the same thing with electrons. Electrons and light, electromagnetic radiation, both appear like they have the ability to be light and particle, or waves and particles simultaneously. So we're going to treat electrons as a wave somehow and let the math work in. So what I mean by a wave, think about just a sine wave. Well, somehow the electron is a sine wave as well as a particle. And its movement around the atom is kind of a wave-like type thing. All right, but to distinguish these, we're no longer going to say these are orbits. We're going to call them orbitals. So even that bookshelf, we're fine to draw that bookshelf because that's much easier than trying to draw what this actual wave itself looks like. And we say that these are the orbitals. These lines represent the basic orbitals we find the electrons in. All right, so what do these look like? Turns out we actually don't know for certain what the electrons look like or what their orbitals look like. And that's really because the only way we could confirm anything would be to influence things. We'd have to actually get, we obviously can't see it. So to study the path of the electron, we would have to influence things like its location. If we wanted to study its location, we have to influence its speed. So we don't have a great idea to know exactly where the electron is on an atom at the exact same time as knowing how fast it's moving. So we actually have to do weird probabilities. What I mean by that, let's say this is the nucleus. We're going to do a calculation with our quantum levels and predict where the electron is. It might be here. And we'll do it again. We'll do it again. We'll do it again. We'll do it again. Do it again. And we're just going to do that a lot. And then we're going to actually plot out where the electron is most of the time. Now, in a very basic orbital diagram or very basic probability calculation, we actually get something that, you see how it kind of looks like the circle? Looks like an orbit? Well, it's not really an orbit. It's not a ring. That's more of a ball. So the electron's found in a sphere around the nucleus. And the darker that color in the middle just means that we're more likely to expect the electron close to the nucleus. Now, if I move up in that energy level, so you know how we had our different quantum levels? So if I say that this picture over here represent my low quantum level, the next one up looks like this, just bigger. That's all it does. Just adds more energy into it. So we have a bigger ball. But it's still going to look like a beach ball. It's a sphere. Now we're going to do some weird things to it because those different quantum levels, they just get bigger and bigger. So got that next little one and the next one, those little 4 different lines we did. These would just be get bigger and bigger orbital balls. All right. So what we're going to do is actually look at some of the weird things that happen to our calculation. So what I mean by our calculation, this was determined by some formula. And I'm just going to leave it as this. So it's an F of whatever. It was a formula to predict where the electron was. We solved it, mapped that simple electron's location, and repeated that process a lot of times to map this probability curve. Well, we're going to do that, but we're going to have to make minor changes to our wave function. The biggest one, we're going to have to move up in our energy levels. That's going to actually change slight characteristics of this calculation. The other thing we find is as we go up, we can actually fold the orbital in on itself. Now what I mean by that, I'm going to go back to this picture. Think about taking that picture and think about it as being a beach ball. And if you put your hand on a beach ball, and let's say you twist this side this way, and over here you twist it the complete opposite way. So you take the 2 ends of the beach ball and you twist them opposite directions. Now, a beach ball probably not going to do much, but if it was a balloon, it collapses on itself. It makes like a little figure 8 with a little balloon twist in the middle. Well, turns out the electrons do that to them to the orbitals as well. There are orbitals that are perfect spheres, but there are also ones that have twists in them. And that's perfectly acceptable and predictable in our wave functions. So we're going to have, turns out there are 4 variables that affect what this looks like. 3 that affect what the orbital appears to be, and 1 that predicts how many electrons are going into it. All right, so let's look at what these 4 functions are. All right, our first one we've already seen. That's those principal quantum numbers. That's the little shells. Now, before we were only drawing 4. Technically, that will go up to infinity, and we could calculate it, but we actually don't see much more than 8 right now. And that's everything on the periodic table. Doesn't really go much above 8. And we call it the principal quantum number. It's related mostly to the energy and the distance from the nucleus. The higher the number, the bigger it is. All right, the second quantum number, we call it the angular momentum quantum number. So I'm going to put these weird parentheses things like. We have the N. The second one we're going to have is an L. And I'm going to put 2 commas there because I said there's 4 things that we're going to put in there. Well, the L talks about that fold. Remember how we said we had the very basic sphere, and we could put a twist in it. Well, that twist is that quantum number that relates to this angular momentum. And if it has no twists in it, L equals 0 means no twists. L equals 1 means we put 1 twist in it. So if you think about it, doesn't L equals 2 imply 2 twists? But we got to put them on different axes. So we're going to twist this right through the middle and make, kind of looks like a 4-leaf clover. And what do you think that one's going to do? It makes 8. I'm not even going to try to draw that. But the orbitals get increasingly complex in how they look. And there's a picture in your textbook to see them all, much better than looking at my drawings of them. But these shapes are what we get when we actually start to modify the orbital. Now, what's interesting, we don't get all of these for every single shell. What I mean by that, when our n equals 1, for instance, there can only be 1 of these, and it's the simplest one. So when n equals 1, there is only L equals 0. So there's just these s orbitals. We actually say 1s. But when n equals 2, we can have 2 of these. We could have an L of 0, and we can have an L of 1. So there are 2 s orbitals, and there are 2 p orbitals. There's not 3 d, because we only have 2 orbitals on that second shelf. Now, theoretically, this goes up. So L is also an integer. It goes up to 4, 5, 6, 7, etc. The reason we stopped at 3 is because we don't see anything use anything more than an f orbital in nature. So mathematically, the next orbital exists, L equals 4, and we can actually draw mathematically what the wave function looks like and then what the actual orbitals themselves look like. It's just that nothing's using them. All right. Our next quantum number is a weird one. All right, so I'm going to explain this with our little p orbital, our second one. You know how we had our s, it looked like a sphere, and I said twist either side, and you get that little dumbbell? Well, what happens if you twist at the top and bottom? Well, it'd look like this. And if you twist it straight in on itself, you'd get another one of these on a different axis. Well, it turns out those twists can be done in different orientations. This next quantum number talks about those orientations. Now, we're not going to try to predict all the orientations. It's a geometrical property that we actually see. It turns out they go up by odd numbers. So there's only one way to draw a sphere, but there are 3 ways to draw that little dumbbell orbital. And the one that made the 4-leaf clover, there are 5 ways. Now, we don't ever really try to draw them. We just need to know that there's 5 of them. And there's 7 of these. And matter of fact, if we were to go on to the next orbital, which is L equals 4, how many orbitals do you think there are? Yeah, there's 9. It just goes up by odd numbers. Alright, now, those 3 fully describe what the orbital looks like. The next one just describes the electrons going into them. So we have N for the principal energy level, L for the shape, M sub L tells us about the orientation, and then M sub S tells us about the electron in there. Are 4 quantum numbers. Now, we will not do a lot with these other than actually talk about some of the relationships that they are, but theoretically, you could take any one of those numbers and throw them into your nice calculator, not a standard, like you need a supercomputer calculator, computerized ones, and you could calculate what the orbitals look like. We're not doing that. That's outside the scope of this class. That's even outside of the scope of general chemistry. But those quantum numbers generate these shapes. So this was actually generated from a very simple, it doesn't matter what the n is. It could have been 1, 2, 3, 4, 5, 6, etc. You would have got the same general area, but the next one had to be 0, and the next one had to be 0. That would have given us this shape. And it doesn't matter what this is either. But at those first 3 quantum numbers were kind of fixed. The n doesn't matter. It could be 1, 2, 3, 4, 5. 1 would be the easiest. And the next 2 had to be 0 to get that sphere. But you simply can put those in and actually calculate what the orbitals look like. Alright, but here's what we're going to do with them. So if I wanted to know something more about the suborbitals, or the orbitals themselves, I'm going to ask a question like this. So what is the maximum number of electrons allowed in a p sublevel of the 3rd principal energy level? So what that's saying, this 3rd principal level, that's saying an n equals 3. That p is talking about our 2nd type of orbital. So we had our s orbitals, which were L equals 0, and p orbitals, which is L equals 1. Well, we really just want to know if you can have an L equals 1 on that 3rd shell. And yeah, you can, because on the 3rd shell, we can have 3 of these. We could even have an L equals 2, which is a D. All 3 of these orbitals exist on that 3rd level. So the p's do exist. So there's at least 1 p orbital. But remember how we had those weird orientations? There is only 1 of these, but there are 3 of these. There have been 5 of this. But this question wants to know how many p orbitals. 3. Now the nice thing is, p's, they're always 3's. So the only way, this answer is either 3 or it's none. The time it would be none is if I had said this was the 1st principal level. If our n equals 1, you have the L equals 0 of S, but there's nothing else because there's only 1 type of shape on that 1st shelf. So if this is at 1st principal level, there isn't a p sublevel. So therefore, it wouldn't hold any electrons. All right. Next little thing we have is how we're going to put these electrons in. It turns out that M sub S can actually help us out. There's only 2 possible answers for an M sub S. It's either -1/2 or +1/2. Now, the halves were actually set up to actually make this math work out later on. We're actually just seeing positive and negative. Matter of fact, if we reduce this to boxes, like if I go back to those p orbitals and say there's 3 boxes, if I put an electron in this first one, I actually just typically see it drawn with an arrow. Up arrow, followed by a down arrow. That's for our 2 different spins. Now where this comes from is it actually turns out in a particular orbital, so these 3 numbers being all set, you can only ever put 2 electrons in that orbital. You can't put 3 in there, only 2 can fit in there. So our s orbital, which is 1 box, could hold 2 electrons. Our p orbital, which is 3 boxes, could hold 6 electrons. D orbital is 5 boxes, 10 electrons, and then 7 boxes could hold 14. And if I go up to the next orbital, L equals 4, it's not 2 more, it's actually 4 more, because we're going up to 9 boxes. So 1, 3, 5, 7, 9 boxes. So it will hold 18 electrons. All right, along with the Pauli exclusion principle, we actually might start adding this to it. So before we asked the number of orbitals, now we want to know how many electrons can go into an orbital. What I mean by that, an f orbital, let's leave off the 4 for a second. If it's just the f orbital, there are 7 boxes. 1, 2, 3, 4, 5, 6, 7. Each box can hold 2 electrons, therefore that can be 14 electrons. Now, the only trick here is having that 4 in front of it. I want to know if an f orbital can exist on the 4th shell. Well, there are, on the 4th shell, there would be s orbitals, there would be p orbitals, there would be d orbitals, and there's f orbitals. There would be 4 different orbitals. So there is a 4f orbital. Alright, but this is not talking about the entire sublevel, is it? It just says orbital. So that 14 applies down here for the sublevel. If I specify the word orbital, I'm actually just talking about a single box. There's only 2 that can go in one of those boxes. The sublevel is all of the orientations of those f orbitals. If it says the word orbital, it's talking about one particular one. If the orbital exists, it only has 2 electrons in it. Now the top one I skipped is kind of weird. It wants to know how many orbitals have an n equal to 2. Alright, so if I have an n equals to 2, I know I have 2 possible shapes. I have an s shape and I have a p shape. If there's an s orbital, there's only 1 box. If there's a p, there are 3 boxes. So that entire orbital can actually carry 1, 2, 3, 4, 5, 6, 7, 8. Okay, electron configuration is just going to be a means that we use to explain how the electrons are. So you remember when we actually first introduced the periodic table, we talked about how the rows talked about the valence electrons. Well, they actually show us a lot more than just the valence electrons. They're actually going to help us see how they're actually arranged in 3-dimensional space and the type of orbital they're in. What I mean by that, a very basic idea. Let's look at, and I'm going to go back to the periodic table. We're going to get something small. We'll go with carbon. Carbon has an atomic number of 6, has a mass of around 12, and it technically has 1, 2, 3, 4, 5, 6 electrons in it. Alright, so carbon has just those 6 electrons. Now, specifically, there are 2 in the lowest energy orbital, the s orbital. The next orbital up from that is the second shell with just an s in it, and the last 2 are in a p orbital. Well, it turns out everything below that on the periodic table, so I go from carbon to silicon, for instance. Silicon has more electrons in it. It just changes that first number. So if I were to look at silicon, what we're going to see is the 2 changes to a 3 and has S2, 3, P2. The N part, the S's and the P's and the valence orbitals are the same when we're in those rows. Alright, so let's talk about how we got this electron configurations, because I wasn't expecting you to follow along with that perfectly yet. We're going to introduce a couple things, because the weird thing is how they fill is not nice and linearly. What I mean by that, I do fill up all of the 1 shell and then all of the 2 shell. And then if you see the 3s, 3p, 3d, they do go up, and 4s, 4p, 4d, 4f, they go up. As you put those different orientations in there, they shift higher in energy. What's very, very odd is I don't fill up the entire 3rd shell before I start filling the 4th shell. See how I go from 3s to 3p, and the very next thing I fill is the 4s orbital, and then I fill the 3d? Well, it's even worse. Look what's filled before the 4f. The 6th shelf. We start filling up the 6th shelf before we finish filling the 4th shell. Alright, well, the order which they filled is predictable based on those orientations, but we're not going to worry about how they're oriented. We're going to actually do something kind of cool. This guy Aufbau showed us how to do this. So all I'm going to do is write down all of our s orbitals in a column, followed by our p's, followed by our d's, followed by our f's. And I just go down. So 1, 2, 3, 4, 5, 6, 7, and then the 2's are next to each other, 3's, 4's, 5. So I make a nice little grid. Once I've made the grid, I start backtracking, and that's what these yellow arrows form. So the very first thing I fill is the 1s orbital, followed by the 2s, followed by 2p, then 3s, and then 3p, 4s. And see how after 4s we come back up here, and that's why we do the 3d after the 4s. After the 3d, 4p, 5s, then 4d, 5p, 6s, etc. Matter of fact, right here is the bottom of the periodic table. If we look on the periodic table, that 7p right there, that is this atom here, number 118. When all of the electrons go into that p orbital, we are at the end of our periodic table, which is why it stops here. But what type of orbital would be next? Well, we can deduce it. It must be 8s. And after that, we'd be coming back over here. Now, I don't have this complete, but there is another orbital here. It's just where our L equals 4. And then we'll have a 6F, and then we'll have a 7D, then we'd have an 8P. But we can predict what they are. Now, here's the interesting thing. In your lifetime, we probably will get a couple atoms made that use the 8s. After that, this is going to start to get blurry because we're getting so high up on those energy levels, these start to mix. So if I back up to that picture, the previous page, these upper levels are very, very all close together. They start to overlap a lot. So you remember how we actually showed those principal bookshelves at first? They look like they're getting closer as we go up. Well, they do in reality. These levels are very close to one another. They start to actually get mixed. The electron can move between those orbitals without very much energy change at all. Alright, so we're going to actually use those electron configuration to show how the electrons go in. We're going to relate that to the orbital diagram, which shows those little boxes we drew. So you remember how we were drawing boxes to represent the s and the p's? Well, if I go back to carbon and talk about that being that 1s2 and 2s2 and 2p2, what I'm really saying is, well, we're going to draw boxes. A box to represent the 1s, a box to represent the 2s, and 3 boxes to represent all the p's. We always draw the entire shell. And if I want to put 2 electrons in there, I'm going to do this. 2 electrons there, I'm going to do that. And here, we're going to kick in this thing called Hund's rule. When I put those 2 electrons in them, I'm going to put them in separate boxes. I won't pair them up until I have to. So if I have 4 electrons in a p orbital, I'd have 3 individually and then 1 left over. What I mean by that, think about this. Which one of these represents nitrogen? So looking at the periodic table, nitrogen is 1 more than carbon. So its electron configuration is very similar to carbon. It's going to be 1s2, 2s2, 2p3. So our 1s is going to be totally filled. We're all good. 2s is going to be totally filled. There's no way that's right then. And 2p is going to have 3 orbitals. Well, this one has 3 and this one has 3. Why is that wrong? Because it started to pair them up when they were still an empty box. We're going to have them unpaired until we can't leave them unpaired. Alright, noble gases help us out on the electron configurations. Alright, so I had actually shown you carbon. Carbon having an orbital of 1s2, 2s2, 2p2. Well, look how crazy this would be if I want to do an electron orbital diagram for, say, chlorine. So chlorine has 17 electrons in it. Look how big this gets, and yet chlorine's not very far on the bottom of the periodic table. So chlorine starts the same way, has the first one totally filled, the second one totally filled, and the third one, the 2p, got 6 electrons in it. Now, I know this because that's only 2, 4, 10 electrons. This represents neon, but chlorine's bigger than neon. After neon, I have my 3s orbital filled, and then I have my 3p orbital, which isn't filled. I only have 5 electrons in that row, and that brings me up to my 17 electrons. All right, as you can imagine, look how long this is getting, and we're only with chlorine. Think about that ogesium, that Aufbau principle that showed all those S's, those P's, those D's, and the F's. We'd have them all written down here. So what we do, so we don't have to write them all, is a better way for me to have drawn chlorine was to back up to the previous noble gas, neon, and put that in brackets. Because that says those guys. Those guys are all part of neon. So after we've passed neon, we just put electrons in the 3p orbital and the 3s orbital. That noble gas configuration helps simplify it so we don't have to write a lot. Now, orbital diagrams, we do the same thing. So the orbital diagrams are those boxes. What I'm going to do for chlorine, rather than draw all these boxes, I'm only going to draw those outermost ones. So I'm going to have a box that represents the 3s orbital and 3 boxes to represent the 3p orbitals. I'll put 2 electrons there, and I'm going to put 5 here. 1, 2, 3, 4, 5. I didn't start pairing until I had to. So I got 2 orbitals that will be paired up in the p block and 1 with a single electron in it. Alright, let's practice some of these. So, best way to do these, or the only way, unless you have somehow the periodic table memorized, you need the periodic table. So hydrogen has just 1 electron. It's in that first thing. That is just a single electron in a 1s orbital. 1s1. Helium, technically right next to it, has 2 electrons in it, but it's still in the 1s orbital. Alright, next thing we're looking at is beryllium. Oops, I meant to just make that bigger. Alright, so beryllium is right here. So the 1s orbital is totally filled. And the next just 2 electrons, we go into an s orbital. So 1s2, 2s2. Alright, fluorine, a little bit further on, these are p orbitals. 1s2, 2s2, 2p5. Now, both those last two, we could have used the noble gas configuration. The 1s2 is actually helium, and so we could have put He in brackets in front of it. But technically, if you think about it, I didn't save myself any time at all with helium, because how hard was it to write helium compared to 1s2? The noble gas configuration will help us on the next one, because sulfur is down another row. So to actually do this electron configuration, I'm going to start with neon. And then after neon, we're going to go down 1, 2, 3, and these are s orbitals, 3s2. And then the next thing I fill is these p's, and I'm going over to sulfur, 1, 2, 3, 4, 3p4. And another thing we can do to check ourselves, see how sulfur should have 16 electrons? Well, we just added 2 and 4 to the 10 of neon, 16. And that's all we have to do on electron configuration. Now, orbital diagrams, we are just drawing boxes. I'm going to erase these because they're in my way to do the electron configuration. Now, electron configuration, though, we're only ever going to actually draw the boxes of the outermost orbital. So I do draw that for the I draw the 1s orbital for both the helium and the hydrogen. 1 electron there, 2 here. But on beryllium, I don't need to draw that 1s orbital. I'm only going to draw the 2s orbital, the outermost orbital, or the highest. And same with fluoride, I'm going to draw the s orbital and then the p block, or the p sublevel. 2, and then 5. And then for S, it's going to look very similar. I need to label these. It's going to look very similar to the top, the one right before it, the fluoride, but it's going to be 3s and 3p. Be 2 electrons here, but only 4 here. Let me move my mouse. Electron configuration and orbital diagram. Keep in mind your tests are mostly multiple choice. You're not going to be drawing orbital diagrams on a multiple choice test. All right, we were just talking about valence electrons at the beginning of this chapter, and we said we were going to relate this stuff to our valence electrons we predicted. But what we just showed on things like carbon technically has 4 valence electrons according to our old rule, and we actually now said, well, those valence electrons, after we get rid of the helium, are in an s orbital and in the p orbital. Well, those highest orbitals are the valence electrons. Everything else are what we're going to call the core electrons. Valence electrons are still the exact same thing. So if I were to ask a question on the test, how many valence electrons, say, sulfur has? You really can just count right across. 1, 2, 3, 4, 5, 6. Has 6 valence electrons. It doesn't change anything to know what type of orbital they are. Now, if I want the electron configuration, that's a little bit more. But the valence electrons are still the same as they were. You just go right across and you can count where they are in the periodic table to get the number of valence electrons. All right, so what we're going to do here is actually see that if I go on a single row on the periodic table, so lithium, sodium, and potassium, lithium, sodium, and potassium, we would have said before they have 1 valence electrons. Well, when we do the electron configuration, we see something interesting. Let's instead of the full one, looking at just the noble gas configuration, if you notice all of these end in S1. The first number's different, but they're all that S1. Well, that's actually how the periodic table is arranged. It has a lot to do with its valence electrons, but it's much more to do with the type of orbital the electrons are in. Even to the point we can actually back up to the periodic table. I'm going to draw it down here. So our periodic table has these weird little sections, and this is our little zigzag over here. But it turns out if we draw some imaginary bars here, this is the s block. These are p orbitals, and these are d's. So bring up our actual periodic table. These first 2 are s orbital atoms. This whole thing over here is the p block. These are the d's. And then see those big, huge, thick lines? Look at that. It doesn't start until 1, 2, 3, 4, 5, 6s. If you back up and look at the Aufbau principle, after 6s, you fill the 4f orbital. These guys down here are those f orbitals. So you will sometimes, and our book has done it before, referred to this as the s block atoms, and these the d block. I've seen that already. When they talked about transition metals, they talked about the d block atoms. Then you got your p block and the f block are down at the bottom. Pretty neat how it's set up. All right. Excuse me. We're going to see that not only is the valence electrons predicting the behavior, the type of orbital they are in. Matter of fact, we get some weird properties happen when we fill up an orbital. So zinc, cadmium, and mercury are all when that d block is totally filled. You actually will sometimes see and hear these guys referred to as the Nobel metals. They're very unreactive in their pure state. They're actually easy to keep pure because of that. And it is because their orbitals are totally filled. And that actually really affects their properties. All right, last little thing we do in this chapter is talk about some periodic properties. Now, what I mean by periodic properties, there are 2 things, and only 2 things, that we can look at the periodic table and tell exactly what the trend is. That's the atomic radii and ionization energy. Now, atomic radii is just the size. And if I were to go to the periodic table, you would probably, gut would tell you that biggest atom is probably the one with the most mass. Well, that's mostly correct. The size does get bigger as we go down on the periodic table. Oh, I didn't mean to zoom in. But as you go down on the periodic table, it gets bigger. Now, what happens that throws that off? Let's think about our... oh, I didn't want that. I don't know how to do anything on my computer. Let's think about what we know about the orbital diagrams themselves. The noble gases over here have the shell completely filled. Well, which shell? It's that latest, greatest shell. So here's the weird thing. Think about the atom itself as like an egg carton. Over here, the egg cartons are totally filled. And matter of fact, once you get to neon, egg carton's totally full. To actually move up to sodium, you have to get out a new egg carton. You have to get up to the next energy level. So it's like having sodium would be, here's neon's bookshelves, totally filled for those first two levels. And to put one more atom in there, you have to create a whole new shelf. And because of that, the biggest ones are to the left. So it turns out, even though the mass doesn't agree with it, the biggest atom in the periodic table is francium, and the smallest is actually helium. And that's the trend. They go that way. Now there are weird little exceptions. I'm going to show you this. See the little hiccups here? This is the size. So you see lithium is big and gets smaller, 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 smaller to neon. Shoots back up, smaller, smaller, smaller. And here's our first hiccup. Potassium, you get smaller, smaller, and smaller, and then there's a little pump, and then you drop back down. But for the most part, it's a nice trend, and we can actually safely say biggest thing is to the lower left, smallest one is the upper right. All right, so that's the trend we're saying. All right, now that you know how that trend, technically you now know the ionization energy trend. All right, so let me define what I mean by ionization energy. Now, ionizing is just making an ion out of an atom. That's either positive or negative. But this is actually technically called first ionization energy. It's a very specific one. It's taking an atom, doesn't matter which atom it is, and ripping a single electron away. All right, think about the periodic table. Which atoms on the periodic table like to give up one electron very easily? Yeah, it's the group 1s. They really like to give it up. And that's actually kind of related to what we just saw on the size. You remember how we were talking about the egg carton? Once you get neon, to get sodium, you have to create a whole new egg carton. Well, if sodium gives up that electron, it's right back to being just like neon. It doesn't have that shelf sticking out there if just one extra book on there. It's a lot more stable. All of our group 1s like to do that. So it turns out the atoms with the smallest first ionization energy are that group 1. Matter of fact, the trend is totally opposite. It gets larger as you go up and larger as you go back across. And we can do a little graph of the data just like we did with our size. Here's the graph with the ionization energy. Our smallest ones by far are those group 1s. And it does get smaller as we go down. And that's really because cesium is just a really, really big atom. That extra electron is really, really, really far away from the nucleus. And then, how do you think helium would like to give up an electron? Clearly it doesn't. It wants to hold on to it really, really well, and it's the one with the highest ionization energy. So the neat thing is, if you know the atomic size, you also know the ionization energy, because they are perfectly opposite one another. Matter of fact, if you look, see how these charts almost look like they're weird inversions? They kind of are, because they're showing the exact opposite things. All right. That finishes it up with this chapter. Plenty of things to practice in this. We jumped all over. Fortunately, we left the advanced calculus out of the quantum theory. If you're interested, change your major to chemistry and you'll have a class called Physical Chem where you'll learn to hate calculus and quantum theory.